Welcome to time dilation. So previously we've seen that in the special theory of relativity, there are two postulates. First of all, that physical laws are the same in all inertial reference frames. And the second, that the speed of light is invariant. So essentially saying that irrespective of the observer's motion, all physics remains the same, and that includes the speed of light, as stated by Maxwell's equation. It depends only on fixed values, and it does not change when the observer is moving. We also looked at Lorenz's transformations, which helped us to change the reference point. In this graph, we can see that the reference point, the observer, is the blue line because it is plotted on the time axis, and the pink line is an object moving relative to this observer. We can use the Lorentz transformation so that the point of view, the observer, is now the pink, and we can see the behavior of the blue relative to that. Time dilation is a consequence of the Lorentz transformation. If we look on this graph at the blue observer, noting that the pink is travelling slightly faster, then when the Lorentz transformation occurs to make pink the observer, then the blue line has been stretched in the y direction. We can tell this because there are 15 data points between the origin and the last one here, and it corresponds with 15 on the y-axis. But if we have a look at those 15 data points on the transformed graph, we can see that the 15th data point is plotting higher than it previously did. So what's happened is that it's been stretched in the y direction, and this is the time dilation. The effect is more pronounced when the pink is travelling closer to the speed of light. Here we can see that the pink is now travelling faster, and when we make that Lorentz transformation so that the pink becomes the observer plotting against the y-axis, we can see that that 15th data point is now plotting much higher. So the greater the difference in velocity between the two objects, the greater the time dilation is. And here is the equation. Here we have the velocity, which is compared to the speed of light. Here we have the time dilation that's observed for that object, compared to the time that has passed for an object that is not moving. We call this proper time. The time that's passed for an object that is stationary. And we call this the dilated time. A very good example of time dilation is the arrival of muons at the surface of the Earth. Here we have the surface of the Earth and the top of the atmosphere. Muons are created when cosmic rays, or particles travelling from space, collide with particles in our atmosphere and decay to produce muons. These muons then rain down towards the Earth, but they have a very short half-life. The distance between where they are created and the surface of the Earth is approximately 10.7 kilometers, and they travel at a velocity very close to the speed of light. Because they are traveling so quickly, they experience time dilation. We can calculate the time it takes for them to arrive at the surface of the Earth from two perspectives: from an observer that is stationary on the Earth, and from an observer who is traveling with the muons. From the perspective of somebody on the surface of the Earth who is not moving and viewing these moving particles, we see that the time taken for them to arrive at the surface is given by the distance that they travel divided by the velocity, which will be approximately 16 half-lives. That means that the number of muons that are arriving at the surface is less than 0.01% compared with the number that were created. If we calculate it from the point of view of the muon, then we see something very different. We need to use the equation for time dilation. And we'll be using proper time because the muon is now the object that is stationary. So from the point of view of the muon, we have this equation. We need to use the other time calculation in here, which is 16 half-lives we get a value for time that is approximately 1 half-life, which means that 50% of the muons that were created at the top of the atmosphere will be arriving down here at the surface. This practical application of time dilation explains the observations that we make. Muons are created in the upper atmosphere, and a large number of them are detected at the surface of the Earth. Traditional calculations led us to believe that the number arriving should be very, very small, but instead we observe that that number is very, very high. Here we can see the blue line and several points plotted out with the observer on the y-axis, the time axis. If we move this line left and right using the Lorentz transformation, then we can see what happens to the time dilation as we get closer and further away from the speed of light. Notice that the orange lines represent the speed of light, moving forwards and moving backwards. Pick one of the points, any point at all, and watch how it moves relative to the horizontal position. With small changes in velocity, we notice that there is almost zero time dilation. But as we shift closer to the speed of light, we notice that they start to raise above that horizontal position, and the closer to the speed of light you get, the more pronounced that effect. And each of those dots is tracing out a U shape that is very flat, close to the y-axis, and becomes almost vertical the closer to the speed of light you get. For a very long time, time dilation wasn't necessary to incorporate into calculations of physics. Newtonian physics only dealt with quite small velocities. It's only more recently that we've begun to understand behaviour closer to the speed of light that we've had to deal with time dilations that are much larger.